Okay, now we are at part C, and we are applying Newton's second law in momentum form to the x direction first. And so for the momentum equation, we do have the second law equation, right? We start from there, so you just write that down. And then think about the free body diagram, see what forces along x direction, and we have none. So that left side will go to 0. That means the change in momentum with time is 0. So if there's no change in momentum, that means momentum is constant along this direction, x direction, and that would mean that momentum is conserved. That means initial and final cases, momentum is the same. And what is that initial and final? That's in this problem, it is the explosion. Right before and right after. Okay, we are now we are looking at just right before and right after, not long time ago or long time after. And then once we write this momentum conservation equation, again, you're not starting with this equation here. You need to always start with this second law and from the equation sheet. And then you're going to think about what pieces you have. Initial cases before explosion, and we only had the puck, so we have only one term. Final is after explosion. There are 3 pieces, 1, 2, 3. So we are labeling appropriately and consistently as well. They're all x's momentum. And thinking about what is given initially, there's no velocity of the puck in any direction, so x component is also 0. That will make the momentum go to 0, because if v is 0, p is 0, right? That's the definition of momentum. Next, we're just going to follow our equation. Left side is 0. We have 3 terms on the right side. We're going to write down what they are. And again, each term is m times v, but we need to be consistent. X1 becomes px1 becomes m1 vx1, and then same things, you need to write the px2 and px3 as well, the same way. After that, you're thinking about how to simplify this again, if there are any 0 terms, and there is one here, because the first piece has only y-axis, right? We showed it here earlier. So this is the first piece and only has y component. That means there's no x component. So that's going to go to 0 in this equation. And we are here. And the other 2 will stay. So masses are not given, but again, we figured out the ratios, and that's what we're going to say. This is M1, this is M2, this is M3. We already found them, especially M3. Assuming there's no mass loss, okay, and that's why the momentum is going to be conserved. We're not changing mass either. And so then we are going to write down things. So Vx1 is 0, Vx2 is negative 15, because the velocity is to the left and positive x-axis is to the right. So you need to also show those negatives, okay, or positives. So you're thinking in terms of vectors. That's really important, because velocity and momentum, they are vectors. And the last thing, this is unknown, so we're just keeping it and then rearranging this equation. Mainly this first term is 0, second term, put it on the other side. The left side was 0 already. That brings another negative, and you already have that negative in the velocity, so it will make it positive. What you're getting is then Vx3 to be positive 10 meters per second. Okay, next part, we are going to work on the y-axis now, and same way, start with the Newton's second law. In the momentum form, sum of Fy is equal to dpy divided by dt. And from the free body diagram, we have no y components. There are no y forces. There are no forces along the y direction, so that's 0. It will give you the change in momentum along y direction to be 0. That would mean the momentum along y direction is constant. Again, that would mean initial momentum along y direction is the same as the final along y direction. And again, once again, initial and finals are defined as right before and right after the explosion. once again, there's no velocity initially, so that first term is going to go to 0, and right side has 3 pieces in it. So we are again writing carefully with proper labeling and being consistent. We're writing p's in terms of mv's. Okay, and then thinking about what can be eliminated if there is any. We realize that the velocity 2 only has x component, so y component is 0. So we got rid of this term. And once again, m1, the mass, m3, the mass of it is written, and vy1 is positive, so you can see that there's no negative here or positive. And now you're solving for vy3. When you put this on the other side, it will introduce a negative sign, so you're going to have a negative result, and that will mean that it's along the negative y direction. When you put the x and y components together, you can write it in unit vector notation, and that's what you get. Just a reminder, there's no k component, there's no z component, so you can also add plus 0 k hat if you like in 3 dimension. When you find the magnitude, so this is the component form, but when you find the magnitude, as you know, we do Pythagorean theorem, so you're going to square each component, add them up, take the root, and in that case we got 14.1 meters per second. Since the components have the same magnitude, you probably realize already that the angle will be 45 degrees, but you can also use tangent and then inverse tangent to find the angle and locate where it is as well, because x component is positive and y component is negative, so you can see that y and x, and remember that these are the x and y components. Okay, so that this is negative and this is positive, which is consistent with what we found. And if they're asking for the angle, you can say that it's below positive x-axis 45 degrees, or you can say negative 45 degrees. That would already mean it's below. Or again, you can also do counterclockwise. You can find this entire angle 315 degrees from the positive x-axis counterclockwise. So again, those are the vector stuff, but this is how you apply momentum conservation. The key thing is you don't start with pi equals to pf. You start with the original equation. Okay, these are the equations that comes from the equation sheet. You gotta show this how you get that. So you're not memorizing the condition. You're using the equation, understanding the condition. If there's no forces along that direction, not external forces, of course, then momentum is conserved. So you understand the condition better this way.